We now turn our attention to what is perhaps the most important aspect of maths in chemistry, exploring the mathematics of change, called calculus. Chemistry is all about change, and we need to be able to handle these changes in our mathematical models. We will cover this over a number of videos, but in this particular video we will go over the background on how one aspect of calculus works. In the course of your scientific studies so far, you will have plotted numerous graphs, and often when plotting graphs you've been asked to find the gradient of that graph. You may have done an experiment to determine the rate of reaction, monitoring the change of concentration of a particular reactant over time, sketched a curve through that data and drawn a tangent to the curve at a particular point to determine the rate of reaction at that time by finding the gradient of the tangent. That's a bit of a mouthful, but this strategy is widely used. If we recall the Lennard-Jones potential that we've examined several times in this video series, a gradient here represents the force between molecules, while in quantum chemistry, the gradient of the wave function is related to the momentum of the particle. A gradient is always found the same way. It is simply a fraction showing how much the graph goes up against how much it goes across. In xy systems, it tells us how much y changes as x varies, or the rate of change of y with respect to x. Going back to the reaction rate experiment, we look at how the concentration on the y-axis changes with time on the x-axis, or to put it another way, the rate of change of concentration with respect to time. The problem that we face is that it is rather imprecise to have to plot a graph, then wiggle a ruler around to find our gradient. If we could identify a process to determine the gradient at a predetermined point, things would be a lot easier. At this point, it'll be easier to see what is happening by going to a simple example, but the principles are the same across all aspects of calculus. Let's think about the harmonic oscillator model for a vibrating molecule, often used to start explorations of infrared spectroscopy. The potential of a vibrating molecule is described by a familiar-looking equation. This is simply a quadratic equation, where r is the separation between atoms in the molecule, and A, B, and C are just constants related to the equilibrium bond length and the force constant of the bond. As you will recall from your high school maths, sketching this should give us a parabola, showing how much energy is stored in the bond as it is stretched or compressed. As this shows potential varying with distance, the same variables as the Lennard-Jones potential, finding the gradient at any point will give us the force between molecules. So let's explore this principle. However, instead of using a tangent, we will just connect 2 points on the parabola with a line. Obviously, this is not going to give us the gradient at the point of interest, but it does give us values for r and v that we know. Sketching our parabola again, we will label 2 points. Point P is where we want to determine the gradient, while point M is our movable point. Think of it as a bead that can slide along the parabola. We're just going to look at the gradient connecting P with M, a piece of string, if you will. The only things we know for definite is the value of r at position P and the distance between P and M. We will call this delta r, meaning a little bit of r. We also know how the potential varies with our interatomic separation. So we know that at this point P, the separation between atoms is r, so we know the potential is equal to ar squared minus br plus c. We also know that at point M, the interatomic separation is r plus delta r. This allows us to then calculate the potential at point M, which we will call v plus delta v. The original potential plus the new additional potential induced by increasing r. Remember, the gradient of this line is the change in v, delta v, divided by the change in r, delta r. So let's calculate v plus delta v. We simply plug our value of r plus delta r into the equation and expand it. This looks quite messy, but remember we want to isolate delta v. So now let's subtract the expression for v from the expression for v plus delta v. There's quite a lot to consider, but this gets rid of the original terms ar squared, br, and c, leaving us with an expression that we can factorize by delta r. Now, we divide both sides by delta r to find the gradient of the line we're interested in. What this has given us is an expression allowing us to calculate an approximation of the gradient at any point r along the curve for a given separation between the 2 points. Let's look at this problem again though. Surely we can get a better approximation for the gradient between the 2 points if we slide the movable point closer to our point of interest. This reduces delta r, but of course we can see the gradient is getting closer to the true value. Surely then we get the best possible result when point M is as close to point P as possible. The problem is that this means delta r becoming 0, and this means that in our fraction we've divided by 0, a practice best avoided in maths. However, if we bring delta r as close to 0 as we possibly can, we create something called an infinitesimal, notated as dr. An infinitesimal is a value so small that there is no value between it and 0. It is as complex a concept as infinity, just at the other end of the scale. However, we can say that as the separation, delta r, tends to 0, the gradient of the plot at that point tends towards 2ar minus b. The additional delta r disappears because it has tended to 0. The mathematical wording we use here is dv by dr, telling us the rate of change of v with respect to r. Remember our initial videos where we have the difference between labeling the symbols and what the symbols actually mean. Here we have a symbol which is more complex, the dv by dr, but what it means is the rate of change, or the gradient, of v with respect to r. Let's now compare this result with our initial equation. Lining up the constant terms a, b and c, we now look at what has happened to the r term. In each case, the index of r has dropped by 1. Even in the case of br, it looks as though the r has disappeared. However, its index has dropped by 1 to r raised to the power 0. This of course causes r to disappear, but the same thing has happened here as happened to the first term. The c term has completely disappeared because it had no dependency on r. Look at the a term. While the index of r has dropped by 1, the whole term has been multiplied by the original power after we've gone through this process. As soon as we recognise this, we see what has happened to the c term. There is no r term here, there's no dependency on r, c is a constant. So the rate of change with respect to r for this term must be 0. This process we have gone through is called differentiation, and what we have found is called the first derivative. The general formulation for differentiation is fairly straightforward and can be done for any two linked variables. Here we have used the linked variables v and r, but now let's look at a general case for x and y. Let's say we have an equation where y equals 6x cubed. We want to find its first derivative. So, remembering what we said previously, the rate of change of y with respect to x, or dy by dx, is equal to the original term. However, we need to reduce the index of the variable x by 1, so this now becomes x squared, and we multiply the whole term by the original index of 3. Our result then is that the first derivative, dy by dx, is equal to 18x squared. Additionally, we said the first derivative. This implies there are others. We can now find the second derivative, which is now the rate of change of the gradient with respect to x. Typically, this indicates how curvy the graph is. We simply apply the same rules, but our notation changes slightly, and we say this as d2y by dx squared. Remember, we reduce the power by 1 to x raised to the power 1, and multiply the whole term by the index of the initial term, now 2. So our second derivative, d2y by dx squared, is equal to 36x. Finally, let's look at the notation. This d notation is widely used and is convenient for demonstrating the process of differentiation. But there are other notations to be aware of. The main one is the function notation. In our original exploration, we looked at the potential of the harmonic oscillator. This can be written as a function v of r, showing how the potential v varies with the interatomic separation r. In the function notation, the first derivative is notated as v prime r equal to 2ar plus b, while the second derivative would be notated as v double prime r equal to 2a. Rates of change are vital throughout the physical sciences, and chemistry is no exception. Any reaction that we do, a system where potential varies with distance, even the Gibbs equation where the Gibbs energy varies with either enthalpy or entropy, all of these and more require an understanding of rates of change and the mathematics required to handle them. The examples we have shown in this video have necessarily been simple ones. However, over the course of the next few videos, we will show how to use differentiation to find the rate of change for more advanced cases. As a result of this video, you should be able to apply differentiation to differentiate simple functions. The derivative of a simple function simply reduces the index by 1 and multiplies the whole term by the original index. In the next video, we will explore the differentiation of special functions, including e raised to the power x, sine x, and cos x. As ever, please leave a comment below on what you think, and we'll see you on the next video.